We can use happy op amp theory to analyze all kinds of interesting op amp circuits, but really it boils down to a couple of very common circuits that we'll use all the time. So let's draw them and evaluate how they work. The first one we've already seen is the non-inverting amplifier. It has one input, one op amp, and two resistors. With all of these circuits, it's not very helpful to memorize these equations because we don't know whoever draw it, did they draw R1 here and R2 here, or did they flip them, did they call them something else? So you should be able to use happy op amp theory to evaluate any of these circuits to go back and derive these equations. But we know that because this is a voltage divider, we're going to see something like the inverse of a voltage divider equation. So it should look something like R2 plus R1 over R1 times V in. We call this the non-inverting amplifier because the sign of V out is the same as V in. And we've made V out bigger than V in by more than 1. So whenever we have a small voltage and we want to make it bigger, we generally use a non-inverting amplifier. This also has the advantage of the input being directly connected to the non-inverting pin of the op amp, which we know no current goes into an op amp. So if we have a voltage here that has a very low capability of driving something, it is a voltage, but it can't really supply any current. This is a good way to buffer our circuit so that we observe this voltage without affecting it, we don't steal any of its current, and we amplify it. And we can make an amplification factor here of 10, 100, 1,000, just based on our resistors. Sometimes, though, we want to have a different sign. So we might have a negative voltage, and we want to turn it into a positive voltage. That's where the inverting input comes in. And it has a slightly different configuration. Here, the non-inverting pin is connected to ground, and our input goes across a resistor to the inverting pin, and we still have two resistors. And the equation becomes negative R2 over R1 V in, where R2 is the feedback resistor, the resistor that goes from the output of the op amp back to the inverting input. So note here, we can have any gains. This gain could be in magnitude less than 1 or more than 1, typically more than 1. But it also inverts, so we have the opposite sign. These are both examples of circuits that have one input and one output, but occasionally we will have other mathematical equations that we want to solve. So something like a summing amplifier can take many inputs and sum them. So we might have two inputs in this case, V1 and V2. And this ends up looking a lot like the inverting amplifier. So each will be applied to its own input resistor, which will go to the inverting side of the op amp. The non-inverting side will go to ground, and there will be a feedback resistor from the output back to the inverting side. Here we'll start to call that feedback resistor RF rather than giving it a number. And each input resistor will have its own unique, each input voltage will have its own unique input resistor. And this equation is negative RF times, in this case, V1 over R1 plus V2 over R2. And of course, you could have many more of these if you just keep giving each input voltage its own resistor. Note that it's also an inverting style op amp. And anytime you see a voltage applied to a resistor that goes to the inverting pin of the op amp, you'll probably guess that the overall equation has a negative sign. Whereas if the voltage is applied to the non-inverting side, the gain is positive. Okay, the last one we'll examine is the differential op amp. This is how we can subtract two voltages. So we would have still two voltages, V1 and V2. And V2 will go to a voltage divider to the non-inverting side of the op amp. V1 will go to the inverting side with a feedback resistor. With 4 resistors, this gets a little complicated. So the equation will take the form V out will be V2 minus V1 And there's a coefficient in front of each of these that depends on these resistors. That simplifies out to be V2 minus V1 when all of the resistors are equal, and gets quite complicated when all the resistors have different values. So I'll let you look up that equation, because I've run out of room to write it. Now, you should be very comfortable using happy op amp theory to evaluate how these circuits work. In this case, the non-inverting side, we were able to use the voltage divider equation and happy op amp theory saying that these two voltages will be equal to solve for V out. In the inverting and summing amplifier cases, we would use the fact that the non-inverting side is ground. So this point here, the voltage at the inverting pin should also read 0 volts. So I'll put that in quotes. 0 is what voltage should be there. 0 volts is usually what you read when you talk about ground. But of course this isn't actually ground. It's not wired to ground. The op amp is trying to force that pin to be at 0 volts. We call that virtual ground. Because as long as the op amp is working and it's happy, that point will be at 0 volts. So then how do we solve for V out? Well, we can say this current that goes through R1 is going to be V in minus 0 over R1. That current can't go into the op amp, so it must continue around this way. Why would it ever go in this direction? Well, this voltage must be negative to pull the current away from 0 volts. So this voltage here is going to be 0 volts minus V out divided by R. And so we know that those currents must be equal, so we use the fact that this current is equal to that current and V over R to solve for that equation. And the same thing happens here, is just now that we have two currents coming in that merge and go that way. The differential is the most complicated to analyze, but not much different than the summing or the inverting. Instead of this being virtual ground, this is now a virtual whatever this voltage is, which is coming from a voltage divider equation here. So instead of this current being V1 minus 0, it's V1 minus whatever this voltage is, which you could solve this voltage divider equation to be that current is the same as this current, and so on.